Hello students, welcome to mathematics class. We know that acceleration vector A of a smooth curve C represented by the vector function r of t has two components. One is the component at, which is called the tangential component of acceleration, and the second one is normal component denoted by an. And we have studied that an is given by the formula an is equal to kappa into v square, where kappa is the curvature, which is given by this formula. Kappa is equal to norm of t dash of t divided by norm of r dash of t. And here v is the speed, that is v is equal to magnitude of velocity vector. And the tangential component is given by dv by dt, that is derivative of the speed with respect to t. And here vector n is the unit normal vector and vector t is the unit tangent vector. Vector n is given by t dash of t divided by norm of t dash of t, and vector t is given by r dash of t divided by norm of r dash of t. In this class, we will derive working formulas for the tangential component at, normal component an, and the curvature. For that, first we consider the velocity vector v dash. We know that, velocity vector v. We know that v is equal to r dash of t. And from this equation, we have r dash of t is equal to norm of r dash of t into vector t. So, r dash of t is equal to norm of r dash of t into vector t. And it is equal to, we know that r dash of t is equal to vector v. So, this is norm of vector v into vector t. Or we have, what is norm of vector v? That is equal to the speed v. So, v into vector t. So, we have vector v is equal to, that is velocity vector is equal to speed into unit tangent vector. That is v bar is equal to v into t. Now, so we have v bar is equal to v into vector t. So, we take the dot product with respect to a. That is, we consider v dot a. We have a is equal to an vector n plus at vector t. So, v dot a is equal to, this is our vector v. Vector v is equal to v vector t. So, v dot a is equal to v vector t dot an into n bar. So, here an is a scalar and v is a scalar. So, this becomes an into v into t dot n plus second term v vector t dot at into t bar. At is a scalar, so we can take outside. So, it is at into v into t dot t. And what is t dot n? T is the unit tangent vector and n is the unit normal vector, and these two vectors are orthogonal. So, t dot n is equal to 0. So, the first term becomes 0, and here we have to find t dot t. T dot t is equal to norm of t the whole square. And what is norm of t? We have t is a unit vector. T is the unit tangent vector. So, since t is a unit vector, norm of t is equal to 1. So, this term becomes at into v. So, we have v dot a is equal to at into v, where at is the tangential component of acceleration. From this, we can find at. We have the formula for at, which is given by dv by dt. So actually AT is equal to dV by dt, and from this what is AT? V dot A divided by V. So AT is equal to V dot A divided by V. And what is V? V is the speed which is given by norm of vector V. So we have the tangential component of acceleration is equal to V dot A divided by norm of V. And this can be written as, we know velocity is equal to r dash of t and acceleration is equal to r double dash of t. So this becomes r dash of t dot r double dash of t divided by norm of r dash of t. So the working formula for the tangential component of acceleration is given by, either you can use this, that is AT is equal to V dot A divided by norm of V, or we can use AT is equal to r dash of t dot r double dash of t divided by norm of r dash of t. Next, we have to find the normal component of acceleration, that is An. For that, we find the cross product V cross A. We have vector V is equal to V into vector t, and vector A is equal to An into vector n plus At into vector t. So here we take the cross product. V cross A is equal to, what is vector V? At into V. Vector V is equal to V into vector t. So V cross A is equal to V into vector t cross the first term An into vector n. So here V and An are scalars. So we can take it outside. So it is actually An into V into vector t cross vector n, plus the second term becomes V into vector t cross At into vector t. Here V and At are scalars. So second term At into V into t cross t. So V cross A is equal to An into V into t cross n. We know that t cross n is equal to vector B, the binormal vector, plus here we have t cross t, which is equal to 0. So second term becomes 0. So we have V cross A is equal to An into V into vector B. So from this we have norm of V cross A is equal to norm of An into V into vector B. An and V are scalars. So this is equal to modulus of An into modulus of V into norm of B. So it is equal to An into modulus of V. What is norm of B? We have studied that this B is a unit vector. So norm of B is equal to 1. And what is modulus of An? We have An is equal to kappa into V square. So here we have the term V square, which is always greater than 0. And what is kappa? Kappa is defined by norm of t dash of t divided by norm of r dash of t. So this is also greater than 0. So An is positive. So modulus of An can be written as An. So this becomes An into modulus of V. So from this An is equal to, we have the formula for An, which is given by kappa into V square, that is equal to norm of V cross A divided by mod V, and mod V means the speed, and speed is given by the magnitude of velocity vector, that is norm of V bar. So we have the normal component of acceleration, that is An. An is the normal component of acceleration, which is given by the working formula norm of V cross A divided by norm of V. So you can compare the two formulas. The tangential component AT is given by V dot A divided by norm of V. Similarly, the normal component AN is given by norm of V cross A by norm of V. Now, AN can also be written in this form because we have AN is equal to norm of V cross A divided by norm of V, and we know that V is equal to R dash of T and A is equal to R double dash of T. So, AN can also be written as norm of R dash of T cross R double dash of T divided by norm of R dash of T. Now, we have the normal component AN is equal to kappa into V square. So, we have kappa is equal to AN by V square, and we have AN is equal to norm of V cross A by norm of V the whole square. AN is equal to norm of V cross A divided by norm of V. So, AN by V square becomes, and what is V? V is equal to norm of V. So, AN by V square becomes norm of V cross A divided by norm of V the whole cube, because we have already in the expression of AN we have norm of V in the denominator. So, that term divided by V square. Again we have V square is equal to norm of V the whole square. So, the denominator, the term becomes norm of V the whole cube. So, kappa is equal to norm of V cross A divided by norm of V the whole cube, and it can be written in this form also because V is equal to R dash of T and A is equal to R double dash of T. So, kappa is equal to norm of R dash of T cross R double dash of T divided by norm of R dash of T the whole cube. Next, we consider an example. The curve traced by R of T is equal to Ti plus half T square J plus 1 by 3 T cube K is said to be a twisted cubic. If R of T is the position vector of a moving particle, find the tangential and normal components of acceleration at any t. Also find the curvature. So, we are given a vector function R of T. We have to find the tangential component, that is AT, and normal component, that is AN. At any time t, also we have to find the curvature kappa. So, we have the formula to find all these AT, AN and curvature. And all these formulas are defined in terms of R dash of T and R double dash of T. So, we find these derivatives. So, we have R of T is equal to Ti plus half T square J plus 1 by 3 T cube K. So, R dash of T means the velocity vector V, which is given by differentiating we get first term I plus Tj plus T square K. Then the second derivative R double dash of T, that is A of T is equal to, again differentiating J plus 2Tk. Now, we know that the tangential component is given by AT is equal to V dot A divided by norm of vector V. So, first let us find V dot A, that is, this is our V dot A. Taking dot product, in the second term there is no term of I. So, here in the dot product first term becomes T into 1, that is T, plus second term T square into 2T, that is 2T cube. So, this is V dot A. Now, what is norm of V? Norm of V is equal to square root of 1 square, that is 1 plus T square plus T square the whole square, that is T raised to 4. So, norm of V is equal to square root of 1 plus T square plus T raised to 4. Now, we just substitute in the formula. So, we get the tangential component of acceleration AT is equal to v dot a by norm of v, which is equal to t plus 2t cube divided by square root of 1 plus t square plus t raised to 4. Next, we have to find the normal component of acceleration an, which is given by this formula, norm of v cross a divided by norm of v. So, first we find v cross a. v cross a is equal to determinant ijk, and second row contains the coordinates of, means the coefficients of vector ijk in the vector v, and we have vector v is equal to, what is vector v? v is equal to I plus tj plus t square k. So, the second row becomes 1t square, that is the coefficients of the vectors ijk in the vector v. Now, third row contains coefficients of the vectors ijk in the expression of a. We have vector a is equal to j plus 2tk. So, here there is no I term. So, third row becomes 0, 1, 2t. Now, expanding this determinant and simplifying, we get t square I minus 2tj plus k. So, that is v cross a. So, norm of v cross a is equal to square root of t raised to 4 plus 4t square plus 1. So that the normal component of acceleration is given by norm of v cross a divided by norm of v, that is equal to, norm of v cross a is equal to square root of t raised to 4 plus 4t square plus 1 divided by norm of v is equal to root of 1 plus t square plus t raised to 4. So, it is equal to square root of t raised to 4 plus 4t square plus 1 divided by t raised to 4 plus t square plus 1. So, this is the normal component of acceleration an. Finally, we have to find the curvature kappa. Kappa is given by the formula kappa is equal to an by v square, where v is the speed, which is equal to norm of v. So, we have kappa is equal to an divided by norm of v the whole square. So, we have an is equal to this term. So, this divided by norm of v the whole square, that is t raised to 4 plus t square plus 1. So, here it becomes t raised to 4 plus 4t square plus 1 the whole raised to 1 by 2 divided by t raised to 4 plus t square plus 1 whole raised to 3 by 2. Because in this denominator, power of this term is equal to 1, and here power of this term is equal to 1 by 2. So, 1 plus 1 by 2, 3 by 2. So, this is the value of the curvature at any time t. Now, we define what is meant by radius of curvature, circle of curvature, center of curvature, etc. So, we have the formula for curvature, kappa. Now, its reciprocal, that is reciprocal of the curvature, that is 1 by kappa. It is called the radius of curvature and it is denoted by rho. So, radius of curvature means rho is equal to 1 by kappa. It is the reciprocal of the curvature. So, this is the formula to find the radius of curvature. Actually, the radius of curvature at a point P on a curve C is the radius of a circle that fits the curve there better than any other circle. And the circle at the point P is called the circle of curvature and its center is called the center of curvature. The circle of curvature has the same tangent line at P on the curve C and its center lies on the concave side of C. Here I have drawn a curve C. So this is our curve C. The curve can be shown in black ink. Curve C. We consider a point P on this curve we have to find the circle of curvature. So, we draw a circle that fits the curve. So, here this is the circle that fits this curve C. Now, so this circle is the circle of curvature and the center of this circle is the center of curvature and its radius is the radius of curvature. So, this is the center of curvature and this distance is the radius of curvature denoted by rho. Also, the tangent line to the curve C at the point P is same as the tangent to the circle at the point P. You can also notice that the center of the circle lies on the concave side of the curve C. So here this part is a concave side. So center of the circle lies on the concave side of C. So I stop my class here. You have two questions to do as an assignment work. The first one is, if r of t is equal to 3 cos t I plus 2 sin t j plus tk is the position vector of a moving particle, find the tangential and normal components of acceleration at any time t. Also find its curvature. And second one, find vector t, vector n and vector b and kappa. Kappa is the curvature for motion of on a general circular helix that is described by r of t is equal to a cos ti plus a sin tj plus ctk. So we have formulas to find all these vectors: unit tangent vector, unit normal vector and binormal vector, which is also a unit vector, and the curvature kappa. Here we have to find the tangential and normal components of acceleration and the curvature. So you can do these two problems easily.